All right, so for our screenshots, what you guys had to do last week, first, you were given a function, and then you had to solve for the inverse. Hopefully, we figured out that what I would do first and foremost is turn that into a y. Then your next step is to rewrite it with the x and the y flipped. And then from there, you're just going to solve for y. So y, add 3 to both sides. And this one's fairly easy. I did that on purpose, so hopefully we didn't panic. X plus 3. So last week you were supposed to put in the function that was given, put in your solved inverse to Desmos, and then put in y equals x. And the y equals x is just that fold line that you're shooting for that it should reflect over perfectly. Some call outs I got from people in the past would be that quadratic functions and radical functions kind of confuse them, but that's because radicals can't live in the negative, so you only get half of the reflection of a quadratic. Or if the radical turns into a quadratic, then you get a full parabola instead of just the half hump. And that's just rules to those two functions. That's the difference as far as looking visually. But there's lots of algebraic ways to do this other than just solving for the inverse. But as we've talked about, we have access to Desmos forever and ever and ever. So what I would do is I would go to Desmos. And if it says, are they functions, so we could do y equals x minus 3 in the first one, and then y equals, and I believe it's today's screenshots that are required. And you'd put them both in, and then you'd put x equals y, and that's just showing that it reflects over that green line. In this case, mine's green. If you also don't know that visually, you can actually tell, like, I'm going to change my points. Get rid of my minor grid lines. I like 1 by 1s. So if you can't tell that this 3, 0 is going to become 0, 3, if that for some reason doesn't look visually pleasing to you, or it's not an easy point like that, I usually go with my x-intercepts and my y-intercepts and see if they do reflect, because they're usually the easiest for me to find. But if you click here, you can get your two tables. I'm going to do it again. Get another table. And again, you should see like where this is 1 is negative 2, it should be negative 2, 1. Where it's positive 2, you should get out that negative 1. So you can see where they do reflect or flip, I should say, inverse of each other. So in this case, at positive 3. So if I go to my table here and I put in a positive 3, I should get a 0 out, which I do. So that means that they are indeed inverses. On your screenshot for today, you did not have to do the tables. What you did need to do is go in here and put in yes, and then take a second screenshot, because in this case, these are indeed inverses. It's kind of cool too if you do make the tables, because you can see the good points. You can click them, and then you can actually not have to sit there and decide whether or not you did it right. But 3, 0, 0, 3, again, if you're looking visually, your negative 1, positive 2 would be positive 2, negative 1. So those are the reflections of those points. So in this case, like we looked on here and solved it, these are indeed inverses. Sometimes you can do it visually, like just knowing sort of inverse operations. I would be hesitant to do so just because you do have the access to Desmos. So this one is x minus 1, and then the negative 3x minus 3. Again, I cannot reiterate enough, you do have Desmos always, so use it. There's been a lot of conversation about skipping a lot of the solving parts of lots of things in Math 3 and really just focusing on Desmos. I do not necessarily think we're going to do that unless I'm told I have to, just because after talking to a couple students who are taking the SAT and ACT recently, they have gotten so reliant on Desmos that they have a hard time switching back to TI-83s or being able to do the math longhand. And SATs and ACTs are kind of important. So as awesome as this is as an option, as I've said before, make sure you do try a little of the like solving part and all that good fun stuff, just so you don't lose that skill altogether. But looking at this guy, so if I do have my green is my x equals y, the black and the purple definitely do not match if I fold it over this green line. So I have like a positive 1, 0, which means at 0, I should have a point here on my black, or my second function should be here. The reflection of this purple would actually be parallel across the green. And then if we were looking for the inverse of, say, our black function, y equals negative 3x minus 3, a good point would be negative 1, 0, which means at 0, negative 1. So these two are inverse coordinates, but not inverse functions because it doesn't hold true. So if I go back over here to negative 2, 3, then that means at 3, I should have a coordinate at negative 2. And in that case, this purple line is not down there. So then you would type in here, no, these are not functions. And then you would screenshot and submit this as far as like today's assignment and expectation. We come back. I'm not going to let me do that. Just kidding. So in this case, these are not because they are not reflections. And it could be because they're not reflections in the graph. It could be you tried the tables. Or again, you could solve it. And if I turn this into x equals y minus 1, to get y by itself, I would add 1 to both sides. And so the inverse is going to be the x plus 1. So this one is much like the one we just did prior. They just gave you something wild and crazy. And I will say, if it's a multiple choice question where you're trying to find the inverse, I have watched students get really confused because looking at it, they try to outsmart it. Again, just go in Desmos and plug it in. If you don't want to actually take one and then solve it, or if it happens to be kind of ugly like these guys, because I've watched people shut down on these, which is why I chose these. Desmos all day if you don't want to do it algebraically. But since we're here and I'm teaching and it's a class, let's solve it algebraically because it is doable. This is the one I was talking about where you're going to get a parabola for the second function, but you're going to get a radical graph for the first function because it's a square root function or square root graph depending on where that you see the name of it for this first one, which is not going to exist in the back half of your parabola when it flips. So seeing the x squared and a square root bar is a good sign that these could be inverses because obviously the inverse of a parabola, which is very curved, and a u is not going to be linear. So if this happened to be f of x equals x minus 9, there's no reason to even go into that conversation. If it is a squared function underneath, it needs a square root in the opposite at minimum. And that still doesn't mean these necessarily are great. In my opinion, the 7 and 9 is a problem already because one doesn't exist in the other. But this is our y, so we're going to flip it. So x equals the square root of y minus 9. We're going to solve for y. So I need to move that 9 over. It's going to be x plus 9 equals the square root of y. To undo the root of something, square rooting, cube rooting, or all the numbers, fourth root, you're going to raise it to that power. When there's not a number in the basement, it is an assumed square root. So we're going to square this guy. So x plus 9 squared equals y. Obviously, this is x plus 7, so that's no good. If you wanted to switch this guy and solve it, like if this was the one that was given first, again, this is our y, we'd end up with x equals, sorry to do parentheses, y plus 7 squared. And the inverse of this guy, we got to get rid of that squared first. If you multiply this through, it's just going to make a mess of trying to get the y by itself because then you're going to end up with y squared and you're going to have y to the 1 power. So as is, it's a little easier to undo. So just like rooting something, you undo it by squaring it. Just like that way, you're also going to undo squaring by rooting it. Sorry, my words are getting tangled. So square root of x equals y plus 7. That just makes all of that go away. I want y by itself, so I'm going to subtract 7. So square root of x minus 7. And I just put my y over here because of space. So it's very similar, the first one and the second one, in their actual correct inverses. But again, the 9 and your 7, the difference in those numbers is another good call out for those. Just because we're here, we go to Desmos so you can see what I was talking about as far as your quadratic versus your square root function. So y equals, and you're going to come down to your keyboard, and you should get a square root of x, and then make sure you're on the outside because if you remember from transformations, this is going to take our radical function and move it down 9 instead of to the right or left 9, which would happen if we put it underneath that root bar. And then our second one is going to be y equals x plus, oops, it's not plus 7 squared. And then our reflection line would be y equals x is what you're going to watch it fold over. Negative 7, 0 means at 0, I should be down at negative 7. If it was going to be, again, we already realized the 7 and 9 is a problem. But this coordinate would exist as its inverse at 0, -7. Your x and your y's are just going to switch. So that blue function would have to have come up here. Or the green function would have had to slide over even further to the 9 if it was going to be the inverse of the blue, like if whichever direction. So again, in this case, like our today assignment, we would just type in the fourth line the word no, take a screenshot where I can see all the fun stuff, and then submit it. Today I did write, I think it was yesterday's assignment, that some people were doing this and then trying to do that, but as a subscript, it won't graph when it has this in the front. Like that quadratic should be up here and it's not. I think it was in today's public service announcements I mentioned turning this into, in this case, you could just use f of x again, or you can turn it into g of x if you want to be able to make the tables and compare them. If they're both f of x, I'm not 100% sure they're going to give you two tables because it's going to get confused, I think. No, I'm not, that is not true, because you can click here. So there's not any reason really you have to name them separately that I can think of off the top of my head, other than just practice and understanding. That's just saying Frank function and this is Gertrude function. So f of x and g of x, it doesn't matter, just notating which one you're looking at. So the inverse function of g of x here, so this is a cube root. So again, just like over here, we're going to undo cube rooting by cubing it, and I'm jumping ahead, sorry. Let's switch those guys first. So this is going to be y. It's going to become x equals the cube root of y plus 2. We need to get the y out from underneath that cube root bar. So we're going to cube everything, which makes that go away. So now I have x cubed equals y plus 2. We want y by itself. The inverse of that addition is going to be subtracting 2 from both sides. So x cubed minus 2 equals y. And in that case, that is what they have right here. So these look good for inverses. And again, let's go check it and make sure. Also, hopefully we already know this, but if you want to close these off for whatever reason, make them go away, you can click the color beside them. I feel like I'm starting to repeat myself, and I'm not sure in what class I'm repeating myself. So it's just a good reminder maybe to make sure we don't accidentally mess up. So cube root is going to be under functions. It's not going to be the square root bar, I believe, if I'm not mistaken. Yep. So this guy, and I think you need to put a 3 in there first, then click this guy. Nope, I told you a story. You do not put the 3 in first. You put the 3 in afterwards. And so that's going to be the cube root of x plus 2, which is a cubic function on its side. And we're comparing it to x cubed minus 2. And then again, your x equals y, or y equals x is your fold line. So you're seeing this 1.26, so this should also be 1.26 here. It is, which is awesome. -2, -2. So you can also see in your coordinates, the x's and the y's are inverses of each other. So that's all you're doing as far as inverse functions. Short of having to solve them, there's not a reason why you couldn't use Desmos to answer any style question I've seen thus far for inverse functions. Logarithmic and exponential functions are the exact same way. They do work as inverses of each other as well. This IXL, and this picture is not great, so I apologize. I thought it would print a little bit better. Find f of -1, so the inverse of -6. So it says f of -1 with a -6. Normally, if this was just f of -6, we would go to where x is -6 and see what the output is. Because this is -1, that is basically saying this is y. So we're going to go to where y is -6, and then we're going to come over and pull our x value, which is going to be -2. So with the -1 up here, this is now we're notating the y place versus our normal function notation when this is the x place. And that's because those coordinates, again, typically switch. So if the inverse of this function, so this is f of x, this is f of x, so this guy, oh, I'm making sure I'm telling you right. Yes, I did this. I don't know why I'm questioning myself. I went and did the IXL to make sure I was doing it right. So the actual function, the inverse, is going to reflect itself. So it would be f of negative 2 would be negative 6 for the actual one. So negative 2 is negative 6. So the new coordinate would be negative 2. I'm saying this all backwards, guys. I'm sorry. I'm over-explaining. This is negative 2, negative 6. The inverse is going to be negative 6, negative 2. So these two are going to be the coordinates that are opposite of each other. Across that again, x equals y line. So these would be the flip coordinates. And so the f of the inverse function at negative 6, what is y? And it would be negative 2. So without having to redraw it or really think it through, you're treating this like the y, because here they switched, because it would be negative 2, negative 6 in the function itself, and then your inverse becomes this as a coordinate. And sorry if I made that worse. I didn't mean to make that worse, for sure. I was hoping to make it very simple. So f of negative 1, in this case we're looking at 1. So f of negative 1 is 1. So f of 1, which is here, the function itself, we're going to go to where the y-axis is 1 and go find it. And it's going to be equals negative 2. And that's because the actual function is negative 2, positive 1, and the inverse would be positive 1, negative 2. So this is the x value of the inverse function, but they're giving you the actual function on the graph. So this is f of x, and this is that negative, the inverse of f of x. So f of negative 1, negative 1. So we're going to go on the y-axis at negative 1 and go over and find, and it's going to be a negative 3. And again, that's because at negative 3, for the actual function graphed, f of x, it's negative 3, negative 1. And so the inverse is going to be negative 1, negative 3. So this is our f of negative 1, and this is f of x here for the coordinates under the table. I did work it all the way up to bonus because I know you guys can earn some bonus points on these guys. So this was your, like, as hard as they got. It was just loose coordinates. It's still the exact same idea. So f of negative 1 is 2 is the one is what we're trying to solve for in this case. So instead of going to 2 on your x-axis, you're going to go to 2 on your y-axis and go look for your coordinate, which should be right here, which is going to be 3. So the actual ones that are graphed, all these fun points, is going to be 3, 2. So the inverse is going to be 2, 3. So you're going to give me out a 3 as that answer. Again, hopefully I didn't make that too much terribly worse. You know, I had the best of intentions. After that, word problems, everyone's favorite. The original couple that you guys had last week and a little bit this week, you're going to have the very basic ones. Very basic ones. So a new car is purchased. So remembering growth and decay, you're going to start your initial amount, 1 plus or minus your rate of change as a decimal, raised to the amount of time we're tracking it. And that's going to give us our output. So that's going to be our growth or decay, depending. If it was decay, it's going to be subtraction. If it's growth, it's going to be addition. The biggest thing people mess up is when they see a decimal, they think this is the rate of change as a decimal, and it is not, because there is percentage behind it. So the first couple ones I gave you are the super, very beginning, basic, the kind you did in Math 1. So a new car is purchased for $17,000. That's our first conversation piece right here, $17,000. That's going to be our A value, because that's what we're going to start with. And then the value of the car depreciates, which means we know we're going to have a decay. So that means we know we're going to have a minus on the inside. We're going to turn that into a decimal, and that's either move the decimal 2 to the left or divide by 100. So our rate is going to be 0.1225 per year. And then per year does matter because we will get into compounding in the next couple of days, which means that it's going to be per day, per week, and that does matter big time. What would the value of the car be to the nearest cent after 14 years? So this is going to be my time. So we're going to write our A. 1 is decay, so we're going to subtract 0.1225, and we're going to raise it to 14th. And this is to the nearest cent, which means we're going to make it to pennies, which I've talked to you guys about too, because that's the most realistic use of decimals, or the most common, I should say, probably, is to actually use them for money. So cent, I think, is a great, the hundredths place, great way to go. And then raise it to the 14th. Should be $2,728.40. And after that 0 is a 3, so we're going to leave it as a 0. And that's your answer for that guy. If at any point it said, back in Math 1 when you did this, if we had an X up here in the 14, like how long would it take for us to get to a certain amount of money, right? For its value to depreciate all the way down to a certain number. And we would have this, and you have an X here. You would plug in your function to start with an X up here, and then go look for your output of this specifically. I find it easier to do in your TI-84s and 83s than necessarily in your Desmos, because Desmos doesn't continue the table all the way down. So you would have to do some guessing and checking if you chose to do it that way in Desmos. Also, though, now that we're in Math 3, if our X is up here, we just have a messy exponential function, and we need to turn it into a logarithmic and then solve. So that's the point of our logarithmic functions as well, is to be able to solve those algebraically at this point. So the second one, again, very simple. We're going to just do a couple more, and then we'll call it quits. A town has a population of 5,000, so that's going to be my A value. That's exactly what we're starting with in our conversation. And grows at 4% every year. 4% is awesome. We're going to change that rate, though, to a decimal. So move it. There's an imaginary decimal back here. We're going to move it 2 to the left, or again, divide by that 100. And then what will be the population after 7 years to the nearest whole number? So it's going to grow, which also means, and I skipped it, sorry, that this is going to be a growth. So we're going to add. So we're going to start with our 5,000, 1 plus, and we're taking our percentage as a decimal, and we're raising it to the 7th power, and then it's asking us how much do we get out. Now, you can plug this in Desmos as well, especially when it's as straightforward as these. I will say that you will see them a couple of different ways. So this is the broken down with that 1 plus, but you will also see it written as this, and you want to raise it to the X, where they go ahead and combine the stuff that's in the parentheses. So they add it or they subtract it, like the last one would have been less than $1. I always think of these as like dollars in the middle. So if it's more than $1, it's a growth. If you find less than $1 inside the parentheses or in the place of B, because it's an A, B raised to the X, if that B is less than $1, then it is definitely decay. And then so your rate of decay is going to be how far, or rate of decay or growth is going to be how far away are you from $1? And then once you take that change, or those pennies and dimes and nickels, you will convert it to a percentage to answer that question. So this one, I think we have to put the y equals. It normally should give us, oh, it's because I have an X. I'm so silly. Sorry. We're going to put a 7 up there, and then we get our answer. 6,579.658, but it did say the whole number, so that 6 is going to round this up, so it's going to be 6,580. And that's because people aren't really measured in decimals. You either have a full person or no people, not a 0.25 of people, because that would be weird. So that would be our answer to that guy. Just to see it where we are, this will be the last one, and we'll call it done for the day, and we'll do compound on Thursday, where we are searching for how long. As soon as you see how long, then we know that our time, that exponent up here, is going to be our variable. So again, starting at the beginning, $3,500 is placed in an account. So that means my A value is going to be $3,500 with an annual interest, that means it's happening yearly, constantly, all the same, of 8.75. Be careful, it looks like a decimal, but it's not. We're going to divide by 100, and we're going to get 0.0875. I almost made the same mistake as lots of students do. Remember, it has to move 2 places, 1 and then 1 more. So we're going to get that 0 in the front. To the nearest tenth of a year, how long will it take for the account value to reach? So this is my output now, $36,700. So the tenth of a year. So we're going to get to our 1 decimal place when we're done with this. So we're going to start with 3,500. We're going to, it's going to add to reach 36,000. So we want to get it from here to here. So it's definitely a growth. Also, most accounts annual interest rate, we're adding money to it. So it's going to be 1 plus 0.0875, or like I said, this could be 10875 without the plus. Our time is unknown, and our goal is 36,700. Now, we know how to solve these at this point, so I'm going to show you how to solve them as logarithmic functions instead of your trial and error like we did in Math 1, because we are now Math 3 students, and we can do that. I am going to switch it to this, so 3,500, 1.0875, raise the t, or you can do x if that makes you happier. The variable doesn't matter. Remember, to be able to switch it from exponential to logarithmic, you need a base, an exponent, and an output by itself. That 3,500 is in the way right now. It is attached by multiplication, so we're going to divide by 3,500 on both sides. Now, I have found that it is best, because we have calculator access, to leave this fraction just as is. It's going to look really messy, but for accuracy, the way you round versus the way I round versus the guy on the EOC that makes the EOC rounds versus the guy in Delta, how they round, is usually just not ideal. And it's a little bit one of those trial and errors. As I've mentioned before, I'm a big fan of staying as accurate as possible and then rounding back instead of making my choice assumption of roundings and then hoping I fall where they want us to. So at this point, these are gone. Now I have a base raised to a power equals an output. So log, our base is going to be 1.0875 because that's the base of the exponent of, and you're going to put 36,700 divided by 3,500 is t, because we're solving for our time. And then we're going to plug this in Desmos. It's probably the easiest place. Again, I've mentioned you can do it in TI-83s and 84s by change of base, or depending on if they are updated with the correct programs, which is just more buttons to remember. So I'm going to go with Desmos because I feel like it's the most user-friendly at the moment for these kind of problems. So we're going to type in, or you can go get your functions, and you will find log. And we do not want to use that one. I just messed up because that's our log base 10 when there's nothing in the basement. Remember, it is an assumed 10. And I saw it and I pushed too fast. Log base A. So that's going to allow us that opportunity to change the base, because the base is that ugly decimal we have. Is it going to let me get down there? 1.0875. And then in those parentheses, you're going to put in your, I call it ugly fraction instead of the rounded decimal. Because again, just for sake of accuracy and making sure you can wiggle around from there. And we have our answer of 28.02 because of the 5 behind the 1. If it's 5 or greater, we always round up. And it said to the nearest tenth, so it's actually you're going to go here, and there's a 1, so it's just 28. So it's going to take us about 28 tenths of a year. I'm sorry, years. 28 years. It's going to take us 28 years. So I had to reread the word problem one more time. But hopefully that makes sense and why your logs and how they kind of tie back to Math 1 when you used to do basic growth and decay. If you need help, obviously pop into tutoring, because I know word problems are everybody's arch nemesis. They're not super bad. Compound interest is new. It will be tomorrow. You'll start it. And so I'll make sure to have some of those ready for Thursday for us to go over as well.